Hello, my name is Jose Rangel, and I'm here with Mario, Sonia, and Robert. Today we will be talking about black holes. So, what are black holes? Black holes are points in space where gravity is so massive that even light cannot escape the area. This is what makes black holes black.
Why is that one red?
Get out of here, Mario, you're not in the scene.
Sorry.
Anyway, it was Albert Einstein who first theorized black holes in his general law of relativity back in 1916. However, it was Carl Schwarzschild who came up with the first principle that describes the black hole. Some people think black holes have to be huge, but theoretically, it could be any size and from anything. So even you could be a black hole.
Even me?
Yes, Sonia, even you. Things can become black holes if condensed into a small size called the Schwarzschild radius. So hey, I hear you want to be a black hole.
No, I'm good.
Well, too bad. With this equation, we can calculate the radius you have to get to become a black hole.
The Schwarzschild equation was created by Carl Schwarzschild himself. In this equation, r is radius, g is the Newtonian gravitational constant, m is the mass of the object, and c is the speed of light. In this case, Sonia is represented as m, 70 kilograms or around 150 pounds.
I do not weigh that much.
Gee, you're calling her fat.
Guys, this is just an example. And these constants discovered by Henry Cavan and the homie Ole Romer are essential to our equation. So, plugging the values into the equation and simplifying the math for you guys, we get 1.3 times 10 to the negative 25, or around 1 nanometer times 10 to the negative 16. So, this is the size Sonia has to become a black hole. Good luck in becoming that size.
Thank you.
So how much force would this generate? If we use Newton's law of universal gravitation, which is stated as F equals gmm or divided by r squared, where F is force in newtons, g is the gravitational constant we used in the last equation, m1 and m2 are both masses of two objects, and r is radius. We could plug in the constant, the black hole's mass, and Sonia's fatness in the equation. We're going to place Sonia 5 millimeters away from the black hole. We plug this into r. With the power of the calculator, we see that a black hole is 5 millimeters away from it, will exert 3,772.5 newtons of force. But what the heck does that mean? In comparison, the Earth is exerting a force of 686 newtons on us right now. If with the force we fall on Earth at a rate of 9.8 meters per second squared, then if the black hole is 5.49 times more than Earth's gravitation, the speed Sonia will be flung at is 53.81 meters per second, or 176.8 feet per second.
In 1973, Stephen Hawking discovered that rotating black holes can evaporate and lose mass thanks to the quantum mechanical properties of empty space.
Pairs of electrons in I-type electrons are constantly appearing and disappearing in space. If this happens near the event horizon, one particle escapes while the other carries negative mass into the black hole to lose mass.
In the formula, T equals 1,256 pi squared times g squared times m to the third power divided by hc to the fourth, where g equals the gravitational constant, which equals 6.67 times 10 to the negative 11th. M is the mass, which equals 2.02 times 10 to the 31st. H is Planck's constant, which equals 6.63 times 10 to the negative 34th. And C is the speed of light, which equals 3.00 times 10 to the 8th to the 4th power. Okay, and then when we plug it into the equation and then plug it into the calculator, we get 2.37 times 10 to the 176th power seconds. To convert it into years, I used dimensional analysis. Shout out Ms. Herzog. And I got 2.37 times 10 to the 176 seconds. And then I got 7.52 times 10 to the 168 years.
There is even an equation to figure out the temperature of a black hole, to know if you should bring a jacket if it's too chilly in there. The formula consists of H, which is Planck's constant, C, which is the speed of light, 16 pi, G, the Newtonian constant of gravity, M for mass, and K for Boltzmann constant. I will be calculating the temperature of a black hole. with a mass of 5.7 times 10 to the 24th power, which is the mass of our planet Earth. Well, mankind's planet. I think Jose is from some other planet. So we plug in the values and the temperature adds up to be 8.28 times 10 to the negative 7th power Kelvin. The end.
Hello, my name is Robert Ayala, and we will be discussing tidal forces for black holes. Now, tidal forces are forces between between two objects that pull on each other. For example, the happy moon and our Earth. Now, the moon uses tidal forces for our waves. Wherever the moon moves around the Earth, that's where the waves will move because of the force pulling the waves towards the direction of the moon. A very happy relationship, I might say so myself, except for the event where the relationship isn't so happy, like in this scenario. But that is not what I'm here to discuss. I'm here to discuss how something like our sun would greatly be disintegrated, well, not disintegrated, but broken down into a black hole. To calculate the acceleration in which an object will break down between a black hole, we'll be using the equation A equals 2g md over r cubed. Now, knowing our sun that has a gravity of 28.2 meters per second, a mass of 1.989 times 10 to the 30th power, a radius of 432,424, and a distance, let's just say the distance between the black hole and the sun is 4 miles. Now we have the equation to how much the atoms of the sun will accelerate as it breaks down into the sucking black hole. Okay, first we'll start out with the easy part. 2 times 28.02 equals roughly about 56.04. And 1.9889 times 10 to the 30th power times 4 equals about 7.955 times 10 to the 30th power. Times all we have together, and we have 4.457 times 10 to the 32nd power. Times that by 2, and we get 8.914 times 10 to the 32nd power. Now, for those of you who are passing out on me, this is what it looks like.
Sun, won't you come? Wash away the rain, black hole sun, won't you come?